So hi again, everyone. Today you will see my struggle to explain different generative methods and their differences. So yeah, first let's start with the simplest problem definition that we could have in this scenario. So we have some data X, and we want to create some nice and controllable distribution over this X, so we would be able to create some this nice missed digits or some more complex data. So yeah, so what are other generative models than the diffusion ones that are currently more in the news? Other generative methods, there are several of them. Here I listed 5, and they could be separated into likelihood-based models that directly learn the distribution of this approximate of the maximum likelihood function then from Bayesian modeling, and likelihood or implicit generative models, which are only GANs, as far as I know. Basically, here we don't model any distribution, we just can pass some vector as the input, and the GAN basically just will generate our output without any distribution. If we're talking for originally how GANs look like, we basically have some data X, we have some data distribution over X, and we have some latent space Z to be used to represent the data. Basically, this is to sample, to represent this vector that goes to the input to the generator. It generates that takes this latent variable Z in given parameters theta g, generates output for us. And discriminator that just evaluates how good this output is. And they play this min-max game when the discriminator punches the generator and generator tries to fool this discriminator. In the ideal scenario, we have the real data in black dots. We have the discriminated distribution in blue. We sample some vectors from Z, and we have the generator distribution green. And over some steps, the discriminator should slowly move the generator distribution to match the original data. But in reality, it rarely works that well, because here we have contrastive learning, and it has a tendency to not converge and fluctuate between discriminator and generator. Also, it was harder to scale, but this year there was released a large GAN model. Also, there could be issues with mod collapse, where, for example, our generator generates already some part of distribution well, and doesn't represent other parts of distribution. This part generates the samples well, but ignores all other samples. And also, if our discriminator is too good, it may not give some gradient signal to train a GAN. But there were obviously attempts to remedy these issues, and the most notable one is Wasserstein GAN. Okay, now about the likelihood-based models. Specifically here, we'll be talking more about setup that is in YE, where we have also have some latent variable Z. And here the ideal scenario would be just take rules from the Bayes formula and find analytically this distribution. But in reality, to do this, we would need to average over all the possible latent space by values. Basically, it makes this untractable, so we couldn't do this in some reasonable time. and we don't have some analytical, may not have some analytical distribution over it. So I will shortly talk about VAIs. I think that most of you are already familiar with them and better than I am, but basically, instead, here what we do not use this distribution that is uncheckable. We introduce our model Q phi that is our encoder and that predicts the parameters of the distribution. And then we have our decoder that takes this latent variable z and generates the output data. Basically, it's similar setting for, well, basically this is why it is called the autoencoder. We have encoder and generator. And it is variable because z is actually a random variable that we predict a distribution to. And here we optimize the elbow loss, evidence lower bound loss, where we have this term that basically this p theta is basically the could be every distribution that we want to. Basically, what the assumptions of in YE is that we cannot represent the original data distribution. We replace it with another one. And this distribution that has forms that we like, it can be specified with this p theta. And this model will learn to match this distribution. So the model here would be QF. It's basically KL difference, Leibniz difference, that looks at how these distributions are, how similar they are. And in this case, we will be forcing QA, our model distribution, to become more similar to the distributions that we think the data is. And this is the reconstruction term is for the generator, so that the data looks like like you want to look. The issue here is that we might be simplifying this original data distribution by not selecting the good distribution of this latent variables that we want to match. Here, short information on the slide about autoencoders. I think with the hype over the large LLMs, everyone knows what they are. But I here inserted one of the earlier models where, well, basically what autoencoders do is we just think that the next, we have just some sequence of these values, and the next value is dependent on the all values that came before it. It worked well in text, but it's harder to work when we try to predict a pixel on images in this scenario. But there are also some modifications to make it bidirectional, like BART for language models. But here is some of the earliest attempts. It's called NATE. Here, basically, this is a small linear network where we mask, where we have the input, this input, and we mask it, and we pass to the neural network, and it predicts the constant. Well, the set with defined length. So basically, it should be the predicted basically here are predicted values, and we use the same weights and pass. Oh yeah, it's autoregressive. Autoregressive, yeah. I remember to change the title of the slide. Sorry. And yeah, even in this simple scenario, they are able to generate some bit realistic data on X. This is the input with some masked values, and this is the output. So now about energy-based models. And they specify this non-normalized negative log probability that is called an energy function. Why they are doing that? Because they don't care about the probability for being tractable, but they still, in the original settings, they have this normalizing constant z0 that makes so the integral will sum to 1, basically this notation. And this energy will have low values when we have the when the model thinks that this high probability that the data is real, and this high values when the model thinks that is low probability that data is real. Training could be done even for this original normalized distribution, but this z term here will make it untractable. So what would they do instead is they basically sample one good point and one bad point. How they do this? They initialize it in a random state and let it move on the function. So, and then basically, so well, they move to the function. So here are some bad point, and if we just sample it and then are moving with for example, with the multicolor method in the gradient of this function, we will end up right here. And then having these points, we will optimize. So this bad point will have high energy and a good point will have low energy. No, this to high and this down. One modification of this method is called score matching. It basically does something similar. So here we have the same definition with the energy function and this term z, but here we learn instead of the simple probability p, we learned its gradient of its logarithm. And taking gradient of this function, we will negate over x, we will negate this term that is untractable and does not allow us to calculate a proper distribution. And now what we can do is that we train our model with this term that is derived from the Fisher information that has very long derivation, but basically is my intuition is correct. It's just make more pushes down on the real points on where they are, and they also use the second derivative here, Hessian. So how, okay, then we change this model, and how do we actually use it? So basically we have this, we change the model to do this, to learn this gradient of the logarithm of probability. And we can use it scores in something called longevity dynamics. So basically we end up in we sample a random point from our distribution, and we can just, we have this vector field, we can move it from, for example, if you here are this example, so example of how it's done. So basically we sample a random point, and then we move it with the gradient with the small steps, and it should end up with the region where this energy is low, and we should get some high quality samples from the distribution. But it turns out that it's actually does not work well. Why? Because the data seems to be gathering in some low dimensional manifolds compared to the full dimension of the data. And there are vast amounts of empty space in this data distribution. If we end up on them, we would not move to the high quality samples. So what is the solution is that was tried and worked pretty well is to add some Gaussian noise on to the original data. So we would enlarge this manifold that is where the low energy data is sitting. It will how it is trained. It's trained with the same loss for every. Here is the variance of the loss. We train with different variants, and the same model with different variants, and the same loss that I previously showed is used for each the variance value. Yeah, it's already starting looking something like diffusion models. And this is here is the example from this blog post of the author of this works, and it shows how it all settles. So basically, we will have, if we have so smaller noise, it won't be distributed more correctly, but we still need to have a probability to get from this areas where there were no data during training. So we should. It's also beneficial to use high levels of noise. And also there was a modification to the score-based generative modeling that includes the stochastic differential equations. Basically, what if we try to adding this noise until we just transform the image to just noise? This can be modeled with stochastic differential equations. Here, this is a drift coefficient, some real some vector valued function. This is the diffusion coefficient, and W is just a random Brownian motion. And for this specific stochastic differential equations, the reverse process looks like this. And here we can see the exact things that the score generative models learn, mainly the gradient of the of the log probability. So this means we could. So this basically means that we could use the score-based model to learn this procedure, and it is also can be simplified to some ordinary differential equations. So we will basically remove the term with the Brownian motion with the randomness, and we can end up with the solution in white. So it basically not as random, but still may lead to the good result. Yes, now finally to the diffusion model. They basically look similar, but here we learn not the gradient logarithm of the probability, but we just learn the parameters of the noise during the diffusion process. So basically here we'll just add noise for time steps t, and in the reverse we try to remove the noise. Basically here is the values that the model learn. This is our model with this parameters data. And this is how we basically visualize the difference. So basically how the data moves, how noise moves. How we could train it? We could train it with a simple function, with a simple formula, as just basically taking some difference between random sampled noise. This is our model. This is the diffusion coefficient that mostly serves as a hyperparameter. But basically, here this is a term for injecting a noise for a timestamp t. There is, so we just don't need to add consecutively for each time step, but we could plug in this formula and generate noise for as it would be for this timestamp for the original image of x0. Here, this is example from the denoising diffusion probabilistic models paper, DDPM, and how it is trained. So basically, we have the original image, we sample some random t, then we generate noise for this t and train our model to estimate the noise that was added. And for sampling, we use our model with parameters and just basically it's the image in previous step, and we just basically with our model generate a noise and remove it. And short summary about this different models. So YS are tractable fast, but we limit the original distribution to this function p that we can choose to be different, but it may all not always be the case that our data is this is a good distribution for our data. Autoencoders are tractable, but they make an assumption that the next steps relies on all previous steps, and it may be slower because depending on the model architecture, we may be like in the context with the current LLMs, we need to get features from the all previous tokens and to get the next one. Energy-based flexible, because we basically can plug in any regression function. We don't have any need for it to be to look like distribution, but since we need to during generation sample data, it may be quite slow, and it also is harder to train. Flow-based I removed from here because I wasn't sure it will all I will have time for them, but basically they learn there are also with large sampling, basically we learn some transformation f of f, and during the encoding pass and during the decoding pass we just inverse this transformation. So basically this transformation needs to be an invertible transformation. About the diffusion, they are flexible, they can be tractable, but they are also slow, but this is solvable with the better new samplers. So I guess it is all.